All right, let's compare answers. So this is the one that we did yesterday, right? So that's that. And okay, next one. Okay, read carefully.
Okay, so this is like just writing out what we talked about on Friday, Tuesday.
Okay, can you read that from where you are? Okay, notice the brackets.
Yes.
Infinity and negative infinity always get parentheses. Because we can't include that endpoint because there is none.
I have a question, because if the bracket includes -3.
Correct.
But at -3 the slope is 0, so it's not really increasing.
Right, I'm going to explain that. That's a complex thought as to why is it increasing even though the slope is 0. Yes.
Okay, just kind of going off what he said, because because technically you're including it on the increasing and the decreasing.
Correct.
So is that going to be just one negative?
Yes.
Okay.
It'll be part of that. All right, and recognize that the reason for a maximum is always the same. A maximum occurs when f prime changes from positive to negative. And minimums always occur when f prime changes from negative to positive. Okay. So, that's good. Number 3. Okay, any questions? That look good? Okay, and the last one. Or this is the graph of f prime. This is a weird one because, look at, the derivative is always positive except for this point where x is equal to 0, which means this function, f of x, this is the graph of f prime, the graph of f of x is always increasing. It increases at different rates, but it's always increasing. Okay? Because the derivative is never negative. Okay? And that's why, again, there's no maximums or minimums, because the f prime never crosses over the x-axis. It never goes from positive to negative or negative to positive, ever. Therefore, you can tell automatically that there's no maximums or minimums. Which is also kind of a signal to tell you that it's either always increasing or always decreasing. All right, I'm going to try to explain a little bit more with this, but I'm going to give you, we're going to play with this particular model a couple of times here, and so this is a good mental exercise. This is the graph of f prime. The green one is always the graph of f prime. Okay? Can you tell me where the function is increasing? It should be increasing from this point all the way over to this point. Okay? Can you tell where the function is decreasing? from over here to over here. Is this point a maximum or a minimum? At x equals, negative 1-ish. It's a minimum. Now watch this. Here's the function. Does this match up with what we said? It's decreasing on the left side. This is where we're looking here. Remember, this was f prime. It says it's all negative. That's where the function is decreasing. It's going down. This is the derivative where the derivative is positive. This is where the function is increasing. Same intervals. The derivative went from negative to positive, which means the function went from decreasing to increasing. Therefore, this is where a minimum occurred. So you can tell a lot about a function looking at its derivative, and that's what the whole point of this thing is. We know how to find a derivative now. Now the question is, what can we do with it? And so that's the first example. All right, let me give you another one. I'm going to modify this a little bit. Okay, look at this function now. This is again f prime. This is f prime. Can you tell me the intervals where the function is increasing? So where is the function increasing? It should be increasing along this spot, and that's it. Okay. Can you tell where the function is decreasing? Function should be decreasing along this region and then along this region. Okay. Next, is this going to be where a maximum occurs or a minimum occurs? Increasing to decreasing, this is going to be where a max occurs. What about this point? Minimum or maximum? Minimum. And what about this one? Maximum. Okay, let's test to see if we got that right. So this is the derivative. Here's the function. Okay. Increasing along the orange. Decreasing along the green. And maximums and minimums. Do we have those right? Yep, we got all of them. Okay? Just by looking at the derivative, you can tell what the function looks like. Yes?
Okay, so like, I understand like where the maximum and minimums are, but how do you know like how, like, I guess how far above or below?
How high up and down it goes.
Yeah, and you said there's like you can like find area and stuff, but like how do you?
Okay. Okay, I'm going to increase this a little bit. So here's the deal on that. First thing is, we recognize that the function, that there is a whole family of functions whose derivative is exactly the same. Because all you have to do is put a plus and then a constant on the end. And that's going to be another function that has exactly the same derivative. So you cannot tell without being given what's called an initial value where to graph it. And so I'm not concerned with that right now. We'll figure that out, but not right now. Second thing is how high up and how much does it increase and how much does it decrease? Well, we can tell it in a relative sense by looking at the area. So, for example, yesterday I said the area that's bounded by the curve of the derivative and the x-axis, that area tells how much the function increases by or decreases by, whether or not it's above or below. This is how much it increases by. This is how much it decreases by. And then this is how much it increases by. And this is how much it decreases by. Okay? Just wish we could figure out that area. Then we have it made.
That's next week.
So, when I graph the function, now, I'm going to try to explain what's going on here. F of x, this is the blue ones now, the function. Remember? F of x increases from here all the way up to here. Okay? The y coordinate increases this much. That number is actually equal to the area that's under this curve. The distance that it goes from here to here, that's the upward, the change. Then the function goes down from here to here, it decreases. The amount that it decreases is equal to this area. So you can tell relative by how much area there is. This amount is bigger than this amount just by looking at it. So you know that the function increases higher than it decreases by looking at the area. Now these are sketches. Okay? So sketches don't have to be perfect. We're getting a relative sense. We can nail everything down with ease after with a little bit more analyzing, but that's the deal. Okay? All right, let's do one more. Okay. Here's my function. This is my derivative. So the question is, whoopsie. One of these days.
Why don't you just take that one down?
Because then it's a big blob. See? Not liking the blob.
Now the way there's stuff is just.
Okay, this time, I did the last two. This time, I want you to talk amongst yourselves, and then I want somebody else to do the markings here and tell me what I got here. Maximums, minimums. Where is it increasing? Where is it decreasing? Okay, help me out here. What's here? Max? I'm just trusting you here. This one? Min? Here? Here? Okay, so then we'll do red. Red is going to be increasing. So increasing, I'm going to do this time. It's going to be increasing on this interval. Increasing on this interval. Increasing on this interval. Do you agree? Decreasing is going to be purple. Decreasing here. Decreasing here. All right? So let's see if this matches up. So here's my function. And I'll take this one off. Does this match up? You can easily see the intervals. Look at all the red intervals. That's where the function is increasing. all of the purple intervals are where the function is decreasing. Max, min, we could tell all that by just looking at the derivative. Make sense? Okay. All right, now, I'm going to hold off the discussion on the increasing with the brackets until tomorrow. Okay, so, because I want to make sure I get to the next thing, but don't let me forget, we're going to do that tomorrow. All right, let's hit the lights. We're going to take some notes. We're going to go straight to 3.1 now. So here we go.
Dang it. Gotta act nice now. Nice.
All right, brand new chapter. This is all about the derivative and applications of the derivative. So we're going to do a little thingy here on some vocabulary, extrema and critical numbers. Extrema. Okay, first thing is let's do critical numbers. Critical numbers are x values in which the derivative is either 0 or undefined. Critical numbers are where the derivative is either 0 or undefined. These are magic places. Okay? Magic places. So let's find a couple. So example 1. Directions are find all critical numbers. And the first one is f of x is equal to 3x to the 4th minus 4x cubed. Okay. Find all the critical numbers of the function. And critical numbers are x values in which the derivative is either 0 or undefined. So what do you think we're going to do? Find the derivative. Okay. So step 1, find the derivative. So now the deal is we have to remember how to do the derivative for any possible function because we're going to now use it. See how this builds? So now f prime of x, that's 12x cubed minus 12x squared. So we found the derivative, and we're finding all the x values where the derivative is either 0 or undefined. So step 2 here is we're going to set the derivative equal to 0. Okay. Step 1, find the derivative. Step 2, set it equal to 0 and solve for x. We're kind of reverse engineering the problem. By forcing it equal to 0, we can find all the x values that make a 0. Okay, so now we just have to solve. So what do we get here? I spy 12x squared times x minus 1. Factored form is really good because it allows you to find the solutions faster. So the only way that this equation can be equal to 0, this expression can equal to 0, is now either if x is equal to 0 or x is equal to 1. It's the only possible way. So therefore, our critical numbers are x equals 0 and 1 for that problem. That make sense? Critical numbers. Okay, let's do another one. F of x, so this is another example. F of x is equal to 2x minus 3x to the 2/3. Again, the directions are the same. Find the critical numbers. Find the critical numbers. And critical numbers occur where the function is either 0 or undefined. Okay, so we got to find the derivative. Two-thirds minus 1 is negative 1/3. So this is what I got for the derivative. 2 minus 2 over x to the 1/3. Did you get that? Okay. So, what are the critical numbers of this thing? Well, first you set it equal to 0. 0 is equal to 2 minus 2 over x to the 1/3. And is there a solution to this? Is it ever possible that 0 is equal to 2 minus 2 over x to the 1/3 for some x value? X equals 1 works. Okay? Now, here's how to solve it algebraically. I'm going to just put this term over on the left side. So it's 2 over x to the 1/3 is equal to 2. And then I'm going to cross multiply. So I get 2 is equal to 2 times x to the 1/3. And then you can divide both sides by 2. And that gives you 1 equals x to the 1/3. Just algebra right there, solving for x. Now technically, the way that you're solving this one is you're raising both sides to the 3rd power. Raise this side to the 3rd, raise this side to the 3rd, and that's where you get x equals 1. So this function, this derivative, is equal to 0 when x equals 1. Okay, but we got to check for both of these. Is there ever an x value where this derivative is undefined? It's 0. You see, if x were 0 right here, we'd end up with 2 minus 2 over 0, which is undefined. So this function has 2 critical numbers as well. They are also 0 and 1, but the 1 came from when the function was equal to 0. The 0 came from when the derivative was undefined. So x equals 0. So we say 2 critical numbers, x equals 0 and 1. Does that make sense? Critical numbers are where the derivative is either equal to 0 or undefined. Now, what's cool is maximums or minimums, if they are going to occur, always occur at critical numbers. Always. They don't occur at any other time. If you're going to have a maximum or a minimum, they're going to always occur at a critical number. That might be noteworthy. You can never have a maximum or a minimum that does not occur at a critical number. Critical numbers are huge.
They can't, like, they can't.
They, maximums and minimums cannot occur at any other value other than a critical number.
Do critical numbers mean anything else, or is it just the maximum? It's like
Great question. The flip side of that is, just because you have a critical number doesn't mean that you have
it's like that
a maximum or a
square-
minimum.
Oh, no.
Right. So just because you have a critical number does not mean that there is a maximum or a minimum. And I'm going to demo that one up here. You got your yawn on there. That was a good one. Okay, back to the picture. Remember this one had max, min, max, min? Where did those occur? It occurred every time that the derivative was 0. So if I said to you, how many critical numbers are listed on this board? You say 4. There's 4 critical numbers. And they're each where the derivative is equal to 0. Now, I'm going to modify this one a little bit. And okay. Now, if you look really close here, if I said to you, how many critical numbers are there in this graph? This is the graph of the derivative. How many critical numbers are there here? This touches only one time. Here and here. How many critical numbers? 2. The 2 places where it hits here. Okay? Are there any maximums or minimums here? No. This is the case. Where, look at, there's 2 critical numbers, but there's no maximums or minimums. Because think of what the graph of this looks like. The blue one is the graph. The function goes up, and then it levels off. Derivative is 0 here. Then it increases again, and then it's 0 again. So this is an example of a case where there's 2 critical numbers, but there's no maximums or minimums on the function because it just levels off. It doesn't go up and then come back down again. See that? Okay, put that in your own words in your notebook. So you're summarizing this. Critical numbers are values in which the derivative is either 0 or undefined. If there's going to be a maximum or a minimum, it has to occur at a critical number, period. But just because it's a critical number doesn't mean there has to be a maximum or a minimum. Okay, here's another derivative. There's an asymptote off to the left, there's an asymptote off to the right at y equals 0. How many critical numbers are there? There's one. Okay, it's an asymptote also down here. At x equals 0, the derivative is undefined. There's no value. There's no point. So there's a critical number at x equals 0. That's kind of like that one over there where it says the function is the derivative is undefined. So the graph of this function looks like this. Okay? This is 1 over x. 1 over x is, does not have a maximum or a minimum at x equals 0. It's just simply undefined. Okay. All right, the last one I'm going to have you take down off the chart here. So there's these things called local and global maximums and minimums. So I want you to sketch this chart right here. There's 4 types of extrema. And then we'll put a sentence here, definition. Okay, let's define extrema, and we'll identify what they look like for local and global. Extrema are x values where the function reaches a highest or a lowest value. They're extreme values. And there's 4 types. We have local, max or mins, and we have global, max or mins. Okay? There's 4 types. On an interval, a global max is the highest value on the function throughout the entire interval. It's the highest peak. It's the global max. The global min is the lowest value on the function across the entire interval. Globals are the extreme high and low of the function. Locals are similar to globals in that you can have maximums and minimums, but they're not the extreme cases. For example, this is referred to a maximum, but it's called a local maximum because it's a high point, okay? It reaches the maximum here, but it's not the highest of all. So local is you can still have a maximum, but it's not the highest. Likewise, the local min is a minimum point, but it's not the lowest min. Therefore, it's just called the local min. Yes.
So you can have multiple locals going one global.
Correct. Then at each of those is a global, because it occurs more than once. So it's okay to have more than one global, but it's the same value, same highest value.
So I'm using the graph you were telling us by looking at the depth and whatever.
Then you can look at it with the area under the curve to find out how high it's going relative to the others.
What if two peaks hit the same height?
Then they're both considered global. Yes?
What if there's a maximum, there's a maximum and minimum in the middle of the graph, but then as the end behavior, the graph just goes straight up?
Okay, great question. On a function, say, that looks like this, okay, let's suppose you had a function that looks like this. This one has local maximums and minimums, okay? This is a local min. This is a local max. This is a local max. This is a local min. This one is the global min. And this graph has no global max. Because you can't put a cap on the end of the function. You can't say, this is the highest value. Because there isn't one. It goes on infinitely. Now, tomorrow we're going to also talk about what happens when you have a closed interval. Okay, when you have a closed interval, then the endpoints can actually constitute a maximum or a minimum as well. Even though there's not a max, it's not an actual max. I'll have to put in that one tomorrow. All right, you have homework now. I'm assigning the first assignment in your assignment guide. So this is page 169. You guys will need this one too. I don't know where those went. Oh, I have them right here. Okay, come and get one. You need one of each of these. There's where it's hiding. So page 169. Let's say do Thursday. Tuesday.
169 is the Tuesday. Next
Yeah.
Tuesday.
So page 169, the first assignment is due Thursday. Today's Tuesday, and then tomorrow we're going to take a look at the next section.